All right, hello, welcome. We're going to do notes on all of 2-6. It's a lot, so get ready, get your paper ready, and take these notes with me. So we're going to talk about rational functions, and we've already done a little bit about rational functions, not too much. But what is a rational function? Well, a rational function is a function, f of x, and basically it has a numerator, which we call n of x, and a denominator, d of x. And n of x and d of x, both of those, n of x and d of x, they are both polynomials. So you've seen these before because we've found the domain and range of them. We've also have found polynomials. We've also have found their asymptotes too by looking at them on the graph on our calculator. So let's take a look at number 1. We need to graph on our calculator and find the domain of the following two functions. So get your calculator out and graph in y1, graph 3 divided by, and don't forget parentheses, x minus 1. Hit zoom 6 to get a standard window. And I'm just going to draw the graph of it really quickly. And we have the graph, and it looks like this. Something like that, and like this, okay? All right, so we've graphed that before. We know that the domain would be all real numbers except when x is 1, and we know that because the denominator cannot be 0 here. So that would be the domain, and that would be the graph. And let's go ahead and talk about limits real quick before we get to part B. So they might ask you something like, what is the limit as x goes to 1 plus? And I know that looks kind of strange for this function, for f of x. And we've never done limits before, and we will do limits at the end of the school year, but they're just kind of trying to get you ready for limits. And what they're doing is they're saying, as you're going out on your graph, or as you're going towards 1 plus, I'm recording here, as you're going from 1 plus, thanks Wyatt, you need to go towards 1. So here's x equals 1, you're going towards 1, and your graph is getting taller and taller all the way up to infinity, okay? The other question they'll say is, what is the limit as x goes to 1 minus? A little minus symbol right here for f of x. And that would be to jump on your graph and go towards 1 from the left side. And as you follow this on your graph towards 1, here's 1 again, then your graph is going towards negative infinity. Okay, so they might ask you things like that. We'll do more limits at the end of the year, and we'll talk about that more too. So let's look at B now, part B. Let's graph this one on our calculator. When you graph this on your calculator, make sure that you do 5x in parentheses divided by x squared minus 1 in parentheses. I'm sure that you can tell by looking at the graph what the domain is, or the function, by what the domain is. You can tell by looking at the graph too. This one has 2 breaks in it. So let's just draw it right here real quickly. So our graph goes like this, and then it looks kind of like a cubic in the middle, and then it goes like this. Okay, so there's our graph, and the domain of this, of course, is all real numbers except for when x is plus or minus 1. That would make the denominator 0. And we're going to talk about this in just a minute, but there are asymptotes at plus and minus 1, vertical asymptotes. And then they're going to ask you again, what is the limit as x approaches negative 1 plus? And that's looking at this and going on our graph towards negative 1 from the right side of our graph. And if you look at what that is, it's right here. I'm going towards negative 1 on the right side. So here's the right, and here's the left. I'm on the right side, and I'm going up towards infinity. And then if you do it again for the other side, you look at the limit as x goes to -1 minus, that would be on the left side of -1. And if you go towards, you're getting closer this way towards -1, your graph is going down to -infinity. Okay, that's why there's an asymptote there. We're going to get into that in just a minute also. Okay, so let's talk about our vertical, horizontal asymptotes, whole zeros of the graph. We're going to do it all. We're not going to graph them yet by hand. We want to learn all the tools we can before we graph by hand. So let's talk about vertical asymptotes. Vertical asymptotes of a graph are always x equals a, some constant. Okay? Don't ever write a vertical asymptote as 5 or 3 or -10. It's x equals. Now, x equals a is a vertical asymptote if the limit as x is approaching a of f of x goes to plus or minus infinity. And we just did that on both of those. We looked at our graph. We were going towards a specific number, 1 or -1, both those times, and our graph was going to infinity or -infinity. Okay. Another way that you can say what a vertical asymptote is you can also say that a vertical asymptote are the zeros of the denominator, zeros of d of x, the polynomial d of x. Now that doesn't happen all the time because what happens is you can get a hole in the graph, and that's when the numerator and denominator have the exact same factor and it reduces out. So usually it's the zeros of the denominator, except when you get a hole in the graph, when there is a hole. Okay? All right, so we'll do some examples and it'll be much more clear in just a minute. Now let's talk about horizontal asymptotes. Horizontal asymptotes are going to be y equals b. Y equals a constant b. And with horizontal asymptotes, there are 3 cases that can happen, okay? And it has to do with the degree of the denominator and the degree of the numerator. The way that you find horizontal asymptotes is you take the limit of your function and x goes out to either plus or minus infinity, you will get a horizontal asymptote of b. So if you went back up to these up here, like let's look at letter B real quick. And I'm going to go ahead and say that I'm going to follow my graph. I'm over here, number 1b, and I'm going to go out towards infinity where x keeps going to infinity, and then I get a horizontal asymptote of y equals 0. Okay, and if I go towards -infinity over here, I also get an asymptote of 0. And we've done those a little bit before. So let me show you three cases that can happen when you want to find a horizontal asymptote. So case number 1, we're talking about the degrees. So if the degree of the numerator of your rational function is, what should we do first? Less than the degree of the denominator. Okay, we're talking about degrees. Then what happens is you will get y equals 0. Y equals 0 will be your horizontal asymptote. Okay, so the numerator is small degree. Denominator is overpowering it. It's like you're taking something like, something small, really small, and then putting it over something really big. Like you're going 0 over 100, and then you're going 0 over 1,000, not 0, like 1 over 100, 1 over 1,000, 1 over 1,000,000. The degree is much bigger, not much bigger, but it's bigger than the numerator, and so what you get is 0. That will approach 0. All right, the second case is when the degree of the numerator is greater than the degree of the denominator. Then what happens here is you will have no horizontal asymptote. You might get a slant asymptote, and we'll talk about that at the very end of this lesson. All right, the third one, number 3, is when their degrees are equal to each other. So the degree of n of x is equal to the degree of d of x. And when you get that, this one's actually the one everyone kind of remembers, you get a horizontal asymptote that's equal to the leading coefficient of the numerator over the leading coefficient of the denominator. Okay? And that's what you get. So those 3 things can happen there. You get y equals 0, you can have no, or you get the leading coefficient over the leading coefficient. So let's take a look at some examples now. Okay? So number 2, find the asymptotes, wholes, zeros of the rational function. So let's go ahead and let's look at this first one. We have f of x equals 5 over x plus 3. So the first thing we're going to do is let's go ahead and find the vertical asymptote of this function. And the vertical asymptote is going to be the zeros of the denominator. So we're wherever the domain, is not good. So this would be at x equals negative 3. X equals negative 3. Okay. Now let's find our horizontal asymptote. The horizontal asymptote follows those 3 cases. So in this case, we have 5 over x plus 3. So the degree of the numerator is 0. The degree of the denominator is bigger. It's 1. And so we would get y equals 0 as our horizontal asymptote. Okay. Wholes will only occur when you have the same, like if we had x plus 3 over x plus 3 and they reduce, then x equals negative 3 would have been a whole, but that doesn't happen here. So that doesn't happen. So there's no wholes in the graph. Wholes would be none. And then we have to find the zeros of the rational function. And the way that you find the zeros is you set it equal to 0 and solve. Okay? So you can cross multiply here if you want to do it that way. You get 0 equals 5. Well, there are no zeros either. None. All right, so that would be the 4 things that you have to find. Okay, let's look at the next one. The next one, vertical asymptote, are going to be any zeros of the denominator. Well, if I take the denominator and set it equal to 0, I only get imaginary solutions here. And so we're not dealing with imaginaries. We're dealing on a real graph. We're looking for real asymptotes. So there would be none. Vertical asymptote, none. All right, horizontal asymptote. Take a look at the horizontal asymptote. The degree of the numerator is 1, degree of the denominator is 2. And so, once again, just like the last one, we get y equals 0. And then finally, to find any wholes in the graph, we would have to factor and see if any factors are equal top and bottom, but they're not. So wholes, oops, I should have done that in the other color. That might be bothering some of you OCD people, huh? Yes, let's go back and do horizontal asymptote, y equals 0. There you go. All right, wholes in the graph, I did that in red. Wholes would be none. And then now we'll do zeros. Zeros, set it equal to 0 and solve. And there's a shortcut here. You can just set the top equal to 0 because that's when you want to find a fraction. When it's equal to 0, it's just when the numerator is 0. So subtract 1 and divide by negative 2. So x equals negative 1/2. That would be a 0 of the graph. That would be an X-intercept, if you will. Okay. All right, let's take a look at the next one now. So the next one, I go to this one and I say, all right, the vertical asymptotes are going to be at x equals negative 5. But that's actually wrong, okay? And I wanted to show you that because a lot of people they'll get in the habit of just finding the zeros of the denominator. But in this case, you can factor this. You can factor this function. Factor the numerator and you get x plus 5 times x minus 5. And in the denominator, we have x plus 5. And what happens is that is not an asymptote. It's a removable, remember when we did discontinuity, it's a hole in the graph. So this is not correct. Vertical asymptote is not x equals 5. Vertical asymptote would be none for this problem. There is a hole in the graph, though, and the hole, well, let's look at the horizontal asymptote first. Horizontal asymptote, the degree of the numerator is bigger than the degree of the denominator. See, I wrote it smaller. N of x is overpowering d of x. N of x means n for none. There's no horizontal asymptote here, okay? See, the x's are getting on top, they're getting bigger and bigger and bigger over something that's smaller. It's just going to go off to infinity, so there's no horizontal asymptote. And then the next thing would be to find the holes in the graph, and we found it. There is a hole at x equals -5, okay? Now, sometimes they're going to ask you for the point where there's a hole in the graph. X is -5, but what's y? Well, you can't go back and plug it into your original equation here because you'll get 0 over 0. But you can go and plug it in here where you've gotten rid of where you're getting 0 over 0. So you plug it into this right here, and you get f of -5 equals -5 minus 5, which would give you then -10. So the hole in the graph would be at the point -5, -10. The funny thing about this graph is you look at it, it looks super complicated. When you graph it, it's actually just a line with a hole in it. Yeah, it's not even one of those rational function looking things. Okay, finally let's do the last one, letter D. I'm going to move it over here. So I have f of x equals x squared plus 2x minus 3 over x squared minus 1. Now, my suggestion would be to start by factoring this. Okay, factoring it is going to help you find any holes in the graph. It helps you also with the domain. So let's factor the numerator. What times what's -3 adds up to 2 would be a +3 and a -1. And then the denominator is just the difference of two perfect squares, x plus 1, x minus 1. So now let's go ahead and talk about all of these things. So let's start with our vertical asymptote. Vertical asymptote is going to be any zeros of the denominator that do not reduce with the numerator. In this case, I can go ahead and I can reduce this out right now. So I know that the vertical asymptote would only be at x equals -1, because that would make this right here 0. And then the horizontal asymptote, ooh, we haven't had one of these yet. I'm glad this one came up. The degree of the numerator and the degree of the denominator are equal to each other. And so the leading coefficient on the numerator is 1. That's the 1 in front of the x squared. And the leading coefficient of the denominator is also 1. And so we get a horizontal asymptote at y equals 1. We haven't had that yet. That's kind of exciting. So then, let's go ahead and find the holes in the graph. The holes occur, remember, where you can reduce. So the hole occurs at x equals 1. But I might ask for a point, okay? And if I ask for a point, then you would need to plug 1 into your function after you've reduced it. So f of 1 equals 1 plus 3 over 1 plus 1. So you get 4 over 2, which is 2. So the hole occurs at the point 1, 2. And then finally, let's find any zeros. The zeros of the graph are going to be when you set this equal to 0 and solve the function equal to 0. But x equals 1 does not count. See, if you set this equal to the numerator, do not count x equals 1 because that's a hole in the graph. It's not going to be a 0. And so we get x equals -3 is our only 0. All right, so that first page took us 20 minutes. That's a long time, right? Yeah, it's a lot of information, I know. So let's go ahead and put these to practice now. We're just going to do a bunch of stuff, a bunch of examples. You've already learned how to do the parts. Now we're going to put them all. All right, so we're on page 2. So we're going to do some graphing by hand. So consider the function f of x equals 3 over x minus 2 and find the following. Vertical asymptote. All right, so we're not worried about any holes in the graph because there's no x minus 2 up top. So the vertical asymptote would be the 0, which in this case would be x equals 2, 0 of the denominator. So x equals 2 is our vertical asymptote, and we can go over here to x equals 2 and draw in our vertical asymptote, which is just a dashed line going up and down. All right, the horizontal asymptote we can label as y equals 0 because we want to look at the numerator, look at the denominator. The degree of the numerator is small, degree of the denominator overpowers it, it's bigger. So it's going to be y equals 0. So I go to y equals 0 and I draw in my, my horizontal asymptote. All right, now let's find the y-intercept. To find the y-intercept, and we didn't do this on the other page, to find the y-intercept of anything, any function, you just let x equal 0 and you can find the y-intercept. So if I plug in f of 0, I get 3 over 0 minus 2. So I get negative 1.5. That's my y-intercept. So I'm going to go to negative 1.5 and graph it right there. All right, the x-intercept would be the zeros of the numerator. So the zeros of the numerator, that's when you let y equal 0 or f of x equal 0. So I would let 0 equal 3 over x minus 2, and you cross multiply and 0 equals 3. So the x-intercept would be none. There's no x-intercept. And you're thinking, of course there's no x-intercept. There's a horizontal asymptote there. That doesn't matter. That is not the case all the time. So don't just think of that. Okay, but this one does not have an x-intercept. All right, and then the domain, which everyone should be pretty good at. You should say all real numbers except for 2. So now let's go ahead and graph this thing. In order to graph this, these problems, these regular rational functions, will usually have 2 branches. And I can tell what one of the branches is so far because I see this point. And it's going to move right along the asymptote, go through that y-intercept there. Didn't really do that good of a job of going through it. And that'll be part of my branch. Now the other part of the branch is you're going to have to maybe work for a little bit. So I would go down here to x equals 3. And I would just plug in x equals 3 into my function to find out what that point would be. So I'd get 3 over 3 minus 2, which would be 3, 1. There's that point. And just from that point, I know that my graph is going to look like this. And there it is. We just sketched the graph of it. And it doesn't have to be perfect. It has to have your asymptotes in there, any zeros, any intercepts. And that would be it right there. All right, let's look at number 4. Here we go. Consider the function 2x minus 1 over x and find the following. First, find the vertical asymptote. So our vertical asymptote is going to be the 0 of the denominator, which is x equals 0. So we'll put that in over on our graph x equals 0. The horizontal asymptote is going to be y equals, and in this case we have the degrees are equal. The degree of the numerator is 1, degree of denominator is also 1, so we get leading coefficient over leading coefficient, which is y equals 2. So there's our horizontal asymptote. The y-intercept is by letting x equal 0. When you let x equal 0, you get negative 1 over 0. Can't have that. There is none. Now, as you can see, there is, right here, a vertical asymptote at y equals 0. Okay, your graph can never touch a vertical asymptote, never. And so you know that if it goes through x equals 0 as a vertical asymptote, it will not have a y-intercept. All right, now let's find the x-intercept. X-intercept is by setting our function equal to 0 and solving. Add 1, divide by 2. Our x-intercept is 1/2. I go over here, put in 1/2. All right, and then the domain, all real numbers except for 0. 0 would make the denominator 0. So we're ready to graph now. And if I look at this one, I have a point right here. That was my x-intercept. And so I know that my graph's going to go right along both of these asymptotes, and it's going to go through that point. Okay, then I have to kind of work for the other one, so I'm just going to plug in a number. I'm going to plug in x equals -1 into my function to find one other point. And I get 2 times -1 minus 1 over -1. And that would give me, what is that? -2 minus 1 is -3 over -1 is +3. So the point is -1, +1, 2, 3. So there's my point. And this is going to go right along the asymptote and right along that one too. And there's my graph. Aren't these pretty? All right, number 5. Now you're thinking, how many more are there? And we have a few more. 5. Yeah. Okay, don't complain. All right, here we go. So consider the function, find the following. Now, let's start. We've got to find the vertical asymptotes. So let's start by factoring. I'm really bummed I'm not here for this. I love this stuff. All right, x over, and we're going to factor. What times what is -8? Adds up to -2. So that would be x minus 4 and x plus 2. Aha, our first one, that's going to have two vertical asymptotes. So our vertical asymptotes occur at x equals 4 and x equals -2. So go to -2 and put in your vertical line at -2, and also go over to 4 and put in a vertical asymptote there. All right, next one. Let's find the horizontal asymptote. Horizontal asymptote, look at the degrees. The degree of the numerator is smaller than the degree of the denominator, so our horizontal asymptote is y equals 0. There you go. Wow, so this broke it up into 1, 2, 3, 4, 5, 6 different parts. Crazy. All right, let me get rid of all those numbers. Do you need a break? No, no break. All right, so here we go. We have to do our y-intercept now. And our y-intercept is by letting x equals 0. And if you let x equal 0, you'll get 0 over 0 minus 0 minus 8, which is just 0. Our y-intercept is 0. You're like, what? You just put a dot on a y on a horizontal asymptote. Are you crazy? No, I'm not crazy. Maybe a little bit, but no, to put that there, that's okay. You can do that. I'm going to show you why in just a minute, if you just wait. All right, now the x-intercept is found by letting y equal 0. So let y equal 0, and I get x over, it doesn't even matter, so x equals 0. My x-intercept is also 0. Ah, there it is. Okay, and then it says draw the graph. Well, I only have 1 point. That kind of stinks. But then it also says find the domain. So the domain, of course, all real numbers. And I always say of course because you guys are good at this and you know all real numbers except for 4 and -2. So let's take a look at our graph. We don't have much. We need to do some work here. So what I want to do is I want to find out what's going on my outer parts here and here. So I need to find out 1, 2, 3, 4. I'm going to plug in x equals 5. So x is equal to 5. That's going to go into my equation. I get 5 over 25 minus 10 minus 8. And I kind of really don't care that much what the number is. I just really care if it's positive or negative, because that'll tell me where I'm at in my graph. And I get 5/7, which is up here. Okay? And that tells me that my graph is going to be up here. Now, you're probably wondering why this dot is here if I have a horizontal asymptote. Well, the horizontal asymptote only affects the graph as I'm going out towards infinity on my graph or out towards negative infinity. And so the horizontal asymptote is not affecting the inner part of this graph, which is between the vertical asymptotes, -2 and +4. All right, so now let's find out a point over here. We'll go to x is -3. and we'll plug that in. And I plug in x is -3, and I get -3 over 9 plus 6 minus 8. And it ends up being a negative number. I really don't even care what that number is, because since we're just kind of sketching the graph, but I know it's negative, and I know that my graph is going to go right along here and right along there. Nice smooth curve, as best you can. All right, so I got the outside parts of the graph. Now, what does the inside part look like? Well, the inside part is going to be one of two things. It's either going to look like it's going to have the shape of a parabola, or it's going to look like a cubic. And it could be an upside down parabola, it could be, you know, a switched cubic, but it's going to be one or the other. So let's plug in some numbers here. You only have to plug in 2. Let's plug in x equals 1 into our equation, and you get 1 over 1 minus 2 minus 8, which is going to give you a negative number. So we're down here, we're negative. Then let's plug in x is -1. And if I plug in x is -1, I get -1 over 1 plus 2 minus 8, which is also, a negative over negative, which is going to be a positive, so I'm going to be up here. And so this graph would look like a cubic, and the asymptotes here and here will affect it. Not the horizontal asymptote, but the vertical asymptote does. And so that would be the graph. Those are pretty complicated when you get, you know, 2 vertical asymptotes, 1, 2. A lot of stuff can happen to your graph. A lot of things happen here. All right, so that was page 2. Now let's go to page 3. Do you need a break? No? Okay, good. Let's go. All right, page 3 of 3. So now we're going to, oh, I got a visitor. Come on in. EDK's here. Awesome. Let's talk to him. I got to pause. All right, he's gone. Okay, so here we go. We're going to find some vertical asymptotes. Let's factor this thing. I know you're dying to factor it, aren't you? So f of x equals x plus 3, x minus 3, and then on the bottom, x minus 3, and x plus 1. Ooh, this one's going to have some fun in it. Cool, finally. All right, so let's take a look. We have a hole in the graph, okay? So we don't have 2 vertical asymptotes like you might have thought we did. We only have 1 vertical asymptote, and that would be at x equals -1. The other one's a hole. So let's go to -1, and let's draw our vertical asymptote in. There it is. Okay, and then we also need to find the hole in the graph. The hole in the graph is going to be at x equals 3. But I need a point for the hole in the graph. So I'm going to plug in f of 3 into where I've already reduced that out. So I get 6 over 4. So that would give me 1.5. So I'm going to go to the point 1, 2, 3, 1.5, and I'm going to draw a hole in the graph. Pretty good. Okay, now let's go to the horizontal asymptote. And leading coefficients, well, the degrees are equal, so leading coefficient of the numerator is 1. Leading coefficient of the denominator is also 1. And so I'm going to draw my horizontal asymptote in at y equals 1. That wasn't very good, was it? Let's undo that a little bit. Okay. So let's try that again. Is that better? A little bit better. Okay. So now we have our vertical asymptote in, our horizontal asymptote in. Let's find the y-intercept. The y-intercept is to let x equal 0. And if you let x equal 0, you will get -9 over -3. So the y-intercept would be 3. So let's see. 1, 2, 3. There it is. Okay, we've got a point on our graph. And then let's find the x-intercept. And the x-intercepts are found, oh man, I ran out of colors. The x-intercepts are found by, let's just use black. by finding the zeros of the numerator, but that are not the wholes in the graph, okay? So 0 equals x plus 3, so my x-intercept would be -3. All right, so 1, 2, -3. Guess what? We don't have to plug any extra numbers in. So let's draw this thing. Okay, we're going to go like this, and then we're going to pick our pen up and go right past that hole in the graph. Make sure I can tell that's a hole in the graph, okay? And then over here, you're going to go along the asymptotes, and that would be it. Oh, that one's so good. All right, the domain, all real numbers, except for 3 and -1. So at -1, we have a vertical asymptote. That is an infinite discontinuity. Now, I didn't ask you this. I'm going extra on you here. And then 3 is at x equals 3. That's a hole in the graph. That is a removable discontinuity. Removable. Okay? All right, last one. Yay for you guys. All right, if the degree of the numerator is 1 degree greater than the degree of the denominator, there will be no horizontal asymptote. Now, we know that. If the degree of the numerator, remember, was bigger than the degree of the denominator, we get none. The n wins, none, okay? But if it's 1 degree greater than, so an x squared over an x, polynomial, or an x cubed over an x squared, then the graph's going to have a, get ready for it, slant asymptote instead. Whoa. All right, so your graph's going to have a slant asymptote. It's very exciting. So let's do number 7, last one. Okay, so we're going to find the vertical asymptote first. Let's first factor this thing, factor it, okay? Just to see if there's any holes in the graph. So we're going to factor an x out. We're left with x minus 1. And then in the numerator, we have x plus 1. All right, so we're clear. There's no holes in the graph. We have a vertical asymptote of x equals -1. So go to your graph over here, and we'll graph our vertical asymptote x equals 1. All right, this one has no horizontal asymptote, okay, but there is a slant asymptote. So let's find the slant asymptote. And here's how you find the slant asymptote. You are going to take x plus 1, which is the denominator, and we're going to divide it into x squared minus x, the numerator. Okay, you can use synthetic division if you want. I'm just going to use long division. So what times x is x squared? That would be x. I get x squared plus 1x. I subtract -1 minus 1 is negative. Wait, did I do that right? X squared minus, oh yeah, sorry, -2x, and then bring down nothing, which is 0. And then what times x is -2x? That would be -2. -2x minus 2, and then you get a remainder of 2. And it doesn't matter what the remainder is. What we're looking for is this right here. That is our slant asymptote. Our slant asymptote is y equals x minus 2. And we all know how to graph lines, so we're going to go to -2. It's our y-intercept, and we're going to count up 1 over 1. And you're going to draw a line there that is an asymptote. And it's a slant asymptote. Okay. Now what happened here is our graph got broken up into 4 pieces. 4 parts. 2, 3, 4. Okay? And we're going to have just one piece in 2 of them. So let's go ahead and find the y-intercept now. The y-intercept is found by letting x equals 0. So you get 0 over 1, which is 0. So the y-intercept is right there at 0. The x-intercept is going to be to find the zeros of the numerator. There are 2 of them. 0 from this factor and 1 from this factor. So 0 and 1. Okay. The X-Intercepts, yeah, oops, I did it in the wrong color. Oh well, please forgive me, it's getting late. 0 and 1. There they are. It's when 0 equals the numerator, minus 1. Okay. The domain, all real numbers except for -1. That's our vertical asymptote. And now we're going to graph. And you're thinking, oh my goodness, how are we going to pick all these points? Well, guess what? This one's pretty basic. We're going to go right along the asymptote. It's going to dip under and then back out and follow the slant asymptote. And then they're always going to be opposite corners of each other for these slant asymptote ones. So it's also going to be a branch down here. Now I know it looks like it's going vertical. It doesn't actually go vertical because then it wouldn't be a function. But it will keep going as close as it can to that vertical line without actually going completely vertical and touching it. So that would be to find your slant asymptote. All right, that's it. I know it's a lot, and I think you can do it. Graph most of them by hand. You got this.